The number of bells on an insulator is not a reliable indicator of voltage. The voltage rating of an insulator depends on the specific design and materials used. Inductive heating can occur in the steel tower when the overhead wires carry high currents. This is because the tower acts as a magnetic core, and the current flowing through the overhead wires induces a magnetic field. This magnetic field can then induce currents in the tower, which can lead to heating. The National Electrical Code, or NEC, does not have specific requirements for inductive heating in steel towers. However, the NEC does require that overhead conductors be properly supported and protected from physical damage. This includes providing adequate clearance between conductors and any metallic structures. Utilities typically design and construct overhead to underground transitions to minimize inductive heating. This can be done by using non-magnetic materials in the tower, increasing the spacing between conductors, or using special techniques to reduce the magnetic field. In addition, utilities may install surge arresters on the overhead lines to protect the underground equipment from voltage spikes. Surge arresters divert excess voltage to ground, reducing the risk of damage to the equipment. There is potential for inductive heating in steel towers where overhead wires transition to underground. However, utilities take steps to minimize this potential by using proper design and construction techniques. When dealing with overhead to underground power line transitions and the potential for inductive heating in steel towers, it's important to consider several key aspects. Firstly, understanding the factors that contribute to inductive heating is crucial. This phenomenon arises due to the alternating current, or AC, flowing through the overhead power lines, which generates a magnetic field around the conductors. When these conductors enter the steel tower, the tower itself acts as a magnetic core. This means that the magnetic field from the overhead lines can induce circulating currents, also known as eddy currents, within the steel structure of the tower. These eddy currents, flowing through the resistance of the steel, generate heat, leading to inductive heating. Secondly, the design and construction techniques employed by utilities play a significant role in mitigating inductive heating. Several strategies are commonly used. One approach involves using non-magnetic materials, such as aluminum or specialized alloys, in the construction of the tower, particularly in areas where the magnetic field is concentrated. Non-magnetic materials have a significantly lower ability to support the formation of eddy currents, thereby reducing heat generation. Another strategy is to increase the spacing between the conductors as they enter the tower. By increasing the distance between the conductors, the magnetic field strength in the vicinity of the tower is reduced, leading to a lower magnitude of induced currents and less heating. Furthermore, utilities may employ specialized techniques to actively reduce the magnetic field around the tower. This can involve the use of shielding materials or the strategic placement of conductors to cancel out magnetic fields. Thirdly, the role of surge arresters in protecting underground equipment from voltage spikes is vital. Surge arresters are protective devices designed to limit transient voltages on electrical systems. These voltage spikes can occur due to various factors, such as lightning strikes or switching operations in the power grid. When a voltage surge occurs, the surge arrestor provides a low impedance path to ground, diverting the excess current away from sensitive equipment. This prevents the voltage from reaching levels that could damage or destroy underground cables, transformers, or other components. Fourthly, while the NEC does not have specific requirements addressing inductive heating in steel towers, it does contain provisions that indirectly relate to this issue. The NEC emphasizes the importance of proper support and protection for overhead conductors. This includes maintaining adequate clearance between conductors and any metallic structures, such as the steel tower. Proper clearance helps to prevent accidental contact between conductors and the tower, which could lead to short circuits or other electrical faults. In addition, the NEC requires that all electrical equipment be installed in a neat and workmanlike manner. This includes ensuring that conductors are properly terminated and that all connections are secure. Poorly made connections can increase resistance, leading to localized heating and potentially creating a fire hazard. Fifthly, estimating voltage levels based solely on the number of bell insulators is generally unreliable. The voltage rating of an insulator depends on various factors, including the specific design, materials used, and environmental conditions. While a higher number of insulators may sometimes indicate a higher voltage, this is not always the case. Therefore, it is essential to consult the manufacturer's specifications or other reliable sources to determine the actual voltage rating of an insulator. Sixthly, the principles of electromagnetic induction, which underlie inductive heating, are fundamental to understanding this phenomenon. According to Faraday's law of induction, a changing magnetic field induces a voltage in a conductor. The magnitude of the induced voltage is proportional to the rate of change of the magnetic flux and the number of turns in the conductor. In the case of a steel tower, the alternating current in the overhead power lines creates a constantly changing magnetic field. This changing magnetic field induces a voltage in the steel structure of the tower, which drives the flow of eddy currents. The magnitude of the eddy currents depends on the strength of the magnetic field, the conductivity of the steel, and the geometry of the tower. Seventhly, the potential consequences of excessive inductive heating in steel towers should be considered. If the heat generated by eddy currents is not effectively dissipated, the temperature of the steel can rise significantly. This can lead to several problems, including reduced mechanical strength of the steel, accelerated corrosion, and potential failure of the tower. In extreme cases, the heat can even ignite flammable materials in the vicinity of the tower, creating a fire hazard. Therefore, it is crucial to implement measures to minimize inductive heating and ensure that the tower remains within safe operating temperatures. Eighthly, regular inspection and maintenance of steel towers are essential for detecting and addressing potential problems related to inductive heating. Inspections should include visual examination of the tower for signs of overheating, corrosion, or structural damage. Temperature measurements can also be taken to identify areas where excessive heating is occurring. If any problems are detected, appropriate repairs or modifications should be made to mitigate the issue and prevent further damage. Ninthly, the use of advanced modeling and simulation techniques can be helpful in predicting and mitigating inductive heating in steel towers. These techniques involve creating a computer model of the tower and the surrounding electromagnetic environment. The model can then be used to simulate the flow of current and the generation of heat under various operating conditions. This allows engineers to identify potential hotspots and optimize the design of the tower to minimize inductive heating. Tenthly, it is important to note that the specific design and construction techniques used to mitigate inductive heating in steel towers may vary depending on factors such as the voltage of the power lines, the configuration of the tower, and the environmental conditions. Therefore, it is essential to consult with qualified engineers and follow industry best practices to ensure that the chosen approach is appropriate for the specific application. In summary, inductive heating in steel towers is a complex phenomenon that can pose challenges for utilities. However, by understanding the underlying principles and implementing appropriate design and construction techniques, it is possible to minimize the potential for inductive heating and ensure the safe and reliable operation of power transmission systems.